put it on the main screen. So we're going to talk about what's an abstract syntax tree, some practical applications, so why should you care what an abstract syntax tree is, and then we're going to zoom in on some transformations that are done in PyTest using the AST. And yeah, the last section is about a brainstorm of ideas that what we could do with the AST. So let's start with the tree part of the abstract syntax tree. So an expression, a simple expression like this one can be represented as a tree. So there's an operation, so multiplication, left-hand side, right-hand side, and then the left-hand side is itself an operation. So this can be seen as this beautiful tree. The root node is a multiplication operator, and yeah, there's the left-hand side that itself is the tree. And so if you had to turn yourself into a computer and evaluate this, you might go from bottom to the top. So you start with 1 is 1, 2 is 2, and then you evaluate the 1 plus 2 subtree, and then you can evaluate the whole tree. So let's look at what it looks like in Python. So you have to take my word for it, but in simple.py it's the same expression that we had before. We can run the AST module as a script, and it prints out this user-friendly output. So we can see that there's a module, which is basically always a top-level element. The module has a body, and there's only a list of one item. And it's an expression. Here we find the tree that we had on the previous slide. So because it's a tree, I think it's best displayed as a tree, so it's a moderately better visualization. And we can see that it's a binary operation, and it has children, so the left-hand side of the binary operation, the operator, and the right-hand side of the binary operation. So in the Python abstract syntax tree, all the nodes, the circles here, are Python objects. So here we see the binary operations, and there's constant and nodes, add. In practice, in real programs, there are many different nodes. There's function definition, if statements, assignments, for loops, so everything that's in the language has a dedicated node, but you don't necessarily need to know them beforehand. So what is the abstract syntax tree? It's a tree of Python objects that represent your source code. It's independent formatting, so there's no information about white space or comments. So if you want to convert back to the original source code, you can't do it exactly, but the semantics is there. So it's a representation of the code that is hopefully useful, and the interesting part is that we can play with it and modify it. So before we focus on the AST, let's talk about the high-level view of how the Python code is executed. So this is to give an idea of the bigger picture. This is a big words slide, so if you don't understand everything, it's fine. I remember when this was new to me, I couldn't make sense of everything, but it's good if you want to dig into some details. So first, Python reads the source code as text. And then there's tokenizing, so it splits the text in relevant words. Parsing, so it uses the Python grammar and syntax to group the words and the tokens together. And from there it constructs an abstract syntax tree, so the structure that we've seen before. Then this tree is, when it goes through a few stages and is converted to bytecode instructions. Maybe you've seen sometimes the PYC files, so this is where bytecode instructions are saved. And then the CPython interpreter executes the bytecode instructions. So I remember when I learned about this, I was like, compilation? What is it? So I thought Python was interpreted. So we can talk about that later, because I wouldn't do it in the main talk. But yeah, this happens when Python code is executed. If this is new to you, don't worry too much about it. We're going to focus on the AST here, so you can understand it without understanding all the stages. So we said it was a useful representation of the code, but how do we use it? You can import AST from a standard library, take our expression for us for a little while again, and parse it, and then we get a module object. So this module is a Python object with attributes that we can play with like a regular Python object. We can dump it, and this is basically what AST does when it's invoked as a script with Python-m AST that we did before. And we can also unparse the nodes. So this is a bit more recent in Python, I think. And Python doesn't need to unparse because transform into AST for execution. So when it has a tree, it can compile it and execute code. But you as a developer, when you make modification on a tree, you're very happy to get it unparsed and see what you did and how it's not really what you meant. So this is very convenient to debug. So there's another API that we'll be using later, is the node transformer. So this is straight from the Python docs on the AbstractSyntax tree. The node transformer is a class that will go through a tree and apply transformation. So it will visit a node and it asks, do you want this node to change? And if you said to change it, then it returns a new node. So this follows the visitor pattern, which means that we define methods like visit underscore and then the type of node that we want to change. So here we visit only the name nodes. So the name nodes are basically variables. So when you use foo or any variable name, that will be a name node. And what it's doing is that it's changing the name node into a subscript node. With that, in this example, I just show what it does. It's either, so it turns the first expression into the second one. So we pass the first expression into an AbstractSyntax tree, and then the tree is transformed by the rewrite name node transformer, which goes through the visits the tree, and for every name node, so every variable, it applies this transformation. So this is a pattern that can be used to modify the AST. Now let's look to more details at motivating use case for AST manipulation in PyTest. So first, maybe when we start, you could say our testing with Python. We don't need a library. The language provides assert. So we can have our hello function or test hello and just run test hello and say test passed if it didn't crash. I think this is very valid. I use that sometimes. I did it basically until the tests start failing. Because then the test fails and all we see is assertion error. So it's telling you it failed, but you don't know what hello, like what the function call produced. So basically, it's not very helpful. And it gets worse too, because when you have that, then all it says is assertion error. Then you have you don't even know what expected is, so you don't know what you expected. So whenever this happens, I'm like, so the computer was supposed to be my friend. You're getting betrayed. So the developer experience is to add print statements and run again. This is why we are developers. So let's try to run it with PyTest. This is an ad for PyTest, but I'm sure many of you use it. It's been around for a while. And it's much nicer. It says it does say the test failed, but it explains why. So it tells you, okay, the result of the call function like hello on world produced this, and it even gives you a diff of the string, which is helpful like, to see exactly what's wrong. So they do it for strings, but also for like, all sorts of Python objects. They just try to make it more helpful to the developer. So how did that happen? Well, PyTest did not execute exactly the code that you provided it, because it ran on the same file. Right? We didn't change the code. So when Python runs on this file, it just produces a dry assertion error, and PyTest can do more. So they modified the code before executing it using AST transformations, so that it would print this nicer error message. So now the question is, could we do it? Like, could we try to do something similar, assuming PyTest doesn't exist? Could we reproduce this behavior? So what would it take to try that? Well, we know that we can modify the AST to run different code. So that's the tool we have at our disposal. Now, how do we want to modify the code? So the code we want to modify is the assert line. But what should it look like? Well, let's say this is what we want, because we're not doing the full PyTest thing, it's just too fancy. What we want, let's say, is to show the results of intermediate computations. Similar to PyTest, just less nice. So when like in the assert square, add a b, there are nested function calls, and we'd like to see like, what is the value of a when this crashes, what is b, what is add a b, and so on. So we see all the intermediate computations and it makes it easier to debug. So if we want to do that, at some point we want to print the values of the intermediate computations. That means we probably need to store them somewhere. So maybe we need to assign these to variables and assign them to variables so we can print them when there's a test failure. So maybe we can do something like replace the assert square and ab with this thing. Just add intermediate variables for all the computations. So add ab and then we square that intermediate computation, and then there's another one for the right hand side. And then our assert statement uses this variable, and when there's an error, we just print out the intermediate computations. So there's just some minor details about this, that we want to print the text for the variables too, so not just the value. So maybe we can use a tuple to store a nice display of what the computation represents, and then when it's printed, it will happen. So if that's what we want, that means we want to change the assert statement into this through AST manipulation. So we'll have an assert node that we want to turn into multiple nodes, or if we move the variable inside the try block, then we can say we turn the assert node into one try except node, but with all these intermediate variables. So this is a bit more difficult than the example from the docs earlier, because this intermediate variable thing, when we have an assert node, we're going to visit call nodes, for instance, like add ab, and we want to assign that to a variable to remember it. But also, so we could replace add ab with a variable like intermediate 1, but we need to declare this variable. And this doesn't happen exactly in the same place. So the variable will be declared before the node that we're replacing. So if we use a regular node transformer on its own, it's going to be, we won't be able to do this, because we will be replacing the node, but we also want to insert a node somewhere else in the tree. So this is not a deal breaker, it's just the tricky part about the code. So if we look at the big steps, we have, like before, we have a node transformer, and we have one method that's visit assert. So before we had visit name to change all the variables, and here we only care about the assert nodes first and foremost. So we only define these variables, this method. The first step that we'll look at later is to collect the assignments. So visit everything that's inside the assert node and collect a list of variables that we will want to define, so we can add them later. And then once the assignments are collected, that was the difficult part, and we can turn the assert into a try except block. So this code might look, if you're not familiar with it, might look a bit foreign, but it's really not. I mean, it's not that complicated. So yeah, we define an except handler node. So it has a type. It handles assertion errors, and the body is a list of print nodes and arrays. So this is what will turn the assert in a try assert, and then on assertion error, print all the intermediate variables, and at the end just raise the original errors. So yeah, at the end we replace it with a try, and that this is basically translating the desired code that we had into AST syntax to construct it. So let's get print nodes here based on the list of assignments. So assuming that we collected the intermediate variables that we want, so we have assignment nodes, and we can, this basically defines also print statements one at a time, just as they would appear in an AbstractSyntax tree. So to do that, obviously, you just look up the documentation for nodes and you construct them one at a time, testing things as you go, and then you forget about the weird syntax. So the trickier part maybe is the intermediate variables transformer. So this one is used inside an assert statement to go through the tree and collect all the calls, all the computations. So if there's a binary operation, we want to collect an intermediate variable as well to remember the result of the computation, so we can show it in the debug log, I think. So we need a list of assignments, and we need a variable counter so we can name our intermediate variables. And then we only care about call and binary operation nodes for simplification. So this is another node transformer, and this is what we do for both call and binary operation nodes. So first we get a variable ID. This is the name of the variable. So we do this using our counter variable and some get-friendly variable name function. The goal is just that the variable ID should be unique, so you don't have conflict between your own variables. So this is basically accounting. And then we say, okay, well, we record as assignments that we remember we want to define a variable with this name, and the value based on this node. So generic visit is just so that it visits the children of this node as well. So when you're visiting a call, make sure it visits children of the possibly nested calls. And finally, instead of so we were in the call node, so a node that represents like a function called add AB, we replace it with intermediate variable 1 that we just defined. So this is an interesting part. As variable name for our intermediate variables, we can actually use this and use AST unparsed node. So if you think about it for some, it might seem weird because AST unparsed node is the source code representation of the node. So it might be like expected -1, which is not really a valid variable name in Python. But it turns out that we can do it because in Python this causes a syntax error, but this is done by the parser, and we are past the parser. We are manipulating the AST, so it's like we are in pseudo mode, and we can do like all the bad decisions that we want. So this is actually useful here because it means that maybe we don't need to store separately, like use a tuple to store a nice description of what the computation represents. We can just stash it in the variable name and use that. So yeah, I wrote, is that a good decision? We can definitely do it. So this is an example name that, like add AB, that's a name for your variable. So it's a little odd, but it's interesting because it shows up again later. So the final output is this. This is not exactly what I promised on the slide before, but accept it if please. So this output, if you squint a little, it seems odd because of the variable name thing. Like if you look at the assert, it looks like intermediate 1 square is a function call. It's a function call on add AB, but that's not actually what gets executed. What gets executed is that the whole intermediate 1 square parenthesis add AB closing parenthesis is one variable. Yeah, and so this basically does the job that we wanted it to, so it prints debug information when there's an assertion error. Yeah. So this might have been a lot of code, especially code on slides at the end of the conference day. But that's basically all of it. That's all of it for a proof of concept that we can reproduce a behavior similar to what PyTest does. So what about PyTest? Like, how do they transform the code? So since I just said this was a lot of code, let's get some more code. This is what you get if you do ast.unparse on the code, the ast transformed by the PyTest assertion rewriter. And it's pretty similar, I would say. So it's similarly hard to read on the screen. There's some weird stuff about variable names, like the @ symbol. I'm pretty sure you can't use that in Python variables, but they can use it here. They do use it in the variable names. And actually they do it on purpose so that there is no conflict possible with the user variables. So because they use variable names that are illegal, there's no conflict with whatever a user might try to put in as a regular name. So yeah, it's a little bit more complicated, but it's not that crazy either when you take it piece by piece. And this is PyTest, so this is a battle testing library that handle all the edge cases and stuff. So I think it's interesting to see that this is something that we can comprehend. So yeah, these are some references for the PyTest part. So if you want to look at the code, this is assertion rewriter, you can import it, and yeah, the code is. I won't claim to understand everything in the assertion rewriter. The code is readable, but they also handle a lot of stuff, so it's. So what else are AST good for? So with the PyTest example, I mean, I really enjoyed it when I learned about it because it shows that it's used in the real world on real tools, but it's also used in interpreters. So if you have a JavaScript abstract syntax tree, so the abstract syntax tree is a representation of the code. There's the Python one, but there are many different formats, and like JavaScript has ASTs, many languages have ASTs. And if you run through the AST and you execute it using Python, you have a JavaScript interpreter written in Python. So you can also do Python interpreter written in Python. It's one way of confusing people. The AST is also used in linters, so like ESLint in JavaScript or Flake8 in Python, for example. In formatters too, like Black, which is super popular. It can also be used for refactoring, and we'll talk a bit more about that later. It can be used for transpiling, so there's Babel in JavaScript to convert like, new syntax to older syntax. So transpiling is converting from one language to another. It's one more word to say compiling. It's also used in template engines like Jinja 2. So I think it's a fundamental concept, not because it's super basic or because it's simple, but because it shows up in a lot of the tools that we use. So in particular, it can be used for automated refactoring. So automated refactoring, you can think of it as a script that takes old code as input and outputs refactored code. Sometimes it's called code mod or code modifier. So some popular tools are PyUpgrade and Django Upgrade. That's for the Django mention. So PyUpgrade and Django Upgrade will run on your code and automatically change it. So maybe in a pre-commit hook or to, for instance, upgrade your Django version. So there are breaking changes in the Django API, and the Django upgrade tool maybe takes care of them to change all the places you use all the APIs and migrate you automatically. And they do that using the AST. So we mentioned the AST doesn't preserve comments or formatting out of the box. So maybe if you're writing your own tool, it might prove a bit, might prove a bit difficult to make these modifications. So for that, there's another type of tree, the concrete syntax tree, basically the cousins of the abstract syntax tree. And they preserve white space and comments, so there's more fluff around it, but it feels similar when you're working with it. So one example is libcst from Instagram. I'm sure there are others I'm interested in, like what you used. I've only used this libcst. So you could use the AST and be careful about how you modify the code. That's what PyUpgrade and Django upgrade do, I think, for performance reasons. But it's probably, I think, using a lib like libcst lowers the bar to entry a little bit. So, if I want to convince you that the abstract syntax tree was a concept that's not doesn't have to be super mysterious and it's used in useful tools, but if you want to use it, maybe a good place is like automated refactoring. So I'll tell you how you don't have to go all in straight away. So say you're migrating from a library version to another. Well, first off, if you know about the AST and you know it might exist, you can look for tools that do it. So sometimes there are friendly developers on the internet and they solve your problem, and if you know to look for it, which is fine. So say you're migrating like SQL Alchemy version 1 to version 2, somebody did it, wrote a tool, you can just use that. Failing that, you can write your own code. So I recommend using a library like libcst to lower the, because it makes it a little bit easier. There are examples, and also you get to write ugly code, because this is code that you're gonna run once maybe on your source files, and then produces the output you want, and you can say, oh look, you go to a manager and say, oh look, I worked very hard this week, made all these changes, all these files, and then you throw away the code maybe. So yeah, and also we mentioned like libcst to preserve formatting, but I would really advise formatting with an external tool so that your refactoring script can mess up everything as long as it doesn't delete your coworkers' comments, and then the formatting tool that cleans up everything. And also you don't have to do all of it. Like if you can write a simple transformer that handles like 2 of the cases that are going to save you a lot of time, that's great. And the complicated cases that where you don't want to go through the details of the ASC, you can just do another way. So yeah, my goal was to show that maybe the abstract syntax tree, I mean, it has a fancy name, and sometimes it might sound mysterious, but it's not really. And it gives you a lot of power for things like automated refactoring. You won't necessarily use it every day, unless you develop a new language, stuff like that. But knowing that it's there, that it powers some of the tools, and it's there if you need it. Maybe next time you have a very boring migration to do at your job, you can turn this into a pretty exciting tech problem that might take you only slightly longer to actually solve. So, this is a personal story probably, but I won't admit it. So this isn't exactly the end of the talk, this is just the end of the structure part of the talk. So we did the serious stuff, and then I wanted to look into different usage of AST and see if it could be used for some more fun stuff. So some people, they use ASTs to bring emojis to Python code. I think the pandas example is great because it's an obvious fit for the emojis. And you can run the code, like you save it to an emoji file, and it runs it and executes like correctly. So the way this works, just because it confused me at start, So Python does not allow emojis. Python doesn't even allow the @ variables. It's terrible. So you can see that they run the file using Python G. So it's not exactly Python running the file, but Python G is just a wrapper around Python, and it replaces, like Python G reads the file, replaces the emoji with boring strings, then it passes the AST with Python. So Python is happy here, this is boring string, and then once the parsing stage is done, it transforms the AST again to inject the emojis back. So similar to what PyTest does with the illegal variable names. Emojis are illegal, but you can sneak them in after the parsing step. So another use is code obfuscation. So like import sys is pretty standard, but maybe this is much better. It does the same thing. So I guess it makes your coworker hurt. So I'm not saying you should want that, but maybe it gives us job security. So this thing is actually useful for it's used in capture the flag events. So security related games or competitions solve challenges, and they use this tool to obfuscate like PYC files that were used in the challenges. And this is my attempt at doing something. So I made that when preparing this talk. For a better assert mechanism, we have PyTest for the rational part of comparing values, but there's no one to help with the emotional part when a test fails. So I thought I'm not so happy about the result, but I thought maybe Claude could help, and so I asked them what they think when the test fails. So all the context about the variables, and it's similar to the PyTest transformation that we did. Just send all the relevant variables to Claude and ask it, how do you feel about that? So to get a live reaction, as if there were pair programming beside us. So it can be the coworker that enjoys debugging. So I'm happy to hear about your bad ideas, good for job security ideas, and also AI, because I don't want to be left behind. And a lot of the AST examples online are actually relatively old. I linked to a 2011 blog post, which is ancient in terms of AI age, but they're still very relevant. So if you have ideas, come and share them with me. I'm happy to talk. Also, it's a great way to get started and learn more about the AST, like doing something a bit fun and without too much pressure. This is about me. This is a fake repository where the slides will go next week sometime, and also some code. And I work as a freelance software engineer. Help teams go fast, ship good software. Yes. So thank you.